history of calculus and how it was derived. And so with that, we looked at the history of calculus. And through this history, we learned that there was an immense, well, not an immense, but there was a lack of rigor. And this brought us into issues with George Berkeley, who didn't like the fact, who didn't like infinitesimals being used, and so forth. And what kind of fixed this whole thing was really there was a whole bunch of people who kind of helped out, but we have Cauchy, Riemann, and finally we have Karl Weierstrass. And what came out of Weierstrass, Riemann, and Cauchy? They all developed the notion of a limit. So we're going to look today at what a limit is. We're going to answer that question, and we are going to just look at the properties of limits, and finally, how does a limit help with calculus? Because there's a lot that we can do with limits have nothing, maybe not nothing to do with calculus, but it's not easy to see that they work on calculus. And so we're going to then trace back as to how do they get into calculus and how does that bring rigor about. So let's get started. A limit can be written as lim, as x approaches a number a on the function f of x. And so limits always deal with functions. And what kind of happens here is we look at a value, in this case a, what is the function value at values really close to a, but never equaling a. And it's such that's what a limit is. And so what a limit did was it got rid of the use of infinitesimals. Instead of calling things infinitesimal or just really small, we just said, or they brought the notion of a limit, which then says, instead of just using these ghosts of departed quantities, as Berkeley called them, we said let's take all values really close to a, but not a. And so that's what they really really did. And there's many properties of these and many things to look at. We can talk about continuity or uniform, but right now we're going to just discuss just how do you work with the limit? What is a limit? And so we're just going to start off by looking at some relatively simple examples and get into other examples of how do you actually calculate what the limit of a function is at any given point. So let's cut that there. Let's just do a couple simpler examples. Let's just do a linear equation. So I could say, what's the limit as x approaches 5 on the function 2x minus 8, whatever you want it to be. And so what you need to do in order to evaluate this, well, we know by plugging in 5, we're going to get an answer out of it. And so essentially, what we could do is we could just take the 5, this value of 5, and we can just insert it right into the x, and we can calculate what the limit value is at 5. And so if we did that, you plug that in, you get 2 times 5, 10, minus 8, the limit value is 2. And so if you're to think about this on a number line or think about this as a graph, you would see that as your x is approaching 5 from either side, you are slowly getting closer to 2. So if I chose 4.999, that's not 5. It's really close to 5, and that's going to be giving me a value that's very close to 2. And same thing if I chose 5.0001, it's very close to 5, but it's not 5. And that will also approach 2. So what does this function do as x approaches 5 from both sides? It's going to equal 2. So that's the limit of this function at 5. And we can change, oops, lost my 2. We can change what this value is. We can say, well, what about negative 5 if you wanted to do that? Well, then your limit would change. And so we would get negative 10, we get negative 18. Okay, so as you look at different spots on the function, you're going to get different values of what the limit is. And one of the things that Cauchy and Weierstrass talked about was just continuity along these. Calculus likes to deal with continuous functions. And so they dealt with whether or not, or they said a function is continuous if and only if there's a limit at each point. So let's continue on with some other types of functions that we can deal with in terms of limits. So that was just a relatively simple example just to get us into the mindset of what a limit is. But let's talk about a different one here. If we have the limit of x, so the limit of a function as x approaches, let's say 4 of the function x squared minus 16 over x minus 4. Now, the thing here is we cannot plug in 4. Because if we were to take 4 and insert it in to the x's, we would get 0 over 0. And that doesn't work, of course, in anything. You can't divide by 0. It's okay that the numerator is 0, but having the denominator 0 really puts us in a pickle. So what we want to do is we will erase all that. And we're not going to equal 4. Okay, remember, the limit means we will not equal 4. So there's another way how we can work this out. Well, thankfully there is. We can factor. We can look at, maybe there's a way to eliminate the denominator, and so we can figure out what is the value of this function as we're getting closer and closer to this value of 4. One way to think of, again, of limits. Number line, this is my x's. As I'm getting closer to 4, what are my values as I get closer to 4 and closer to 4 without ever equaling 4? So that's what this does. Okay. So we can factor this. So this is equal to the limit of x as it approaches 4, x minus 4. This is the difference of squares. Just factor straight down. Put the denominator in brackets as well, and we can see that the x minus 4s both cancel off. They are equal. And so we now have the limit of x as x approaches 4 of x plus 4. And now we get back into what we just looked at on the previous page, where now we can just take this value of 4 and we can just insert it straight in, and we would get the value of 8. So if we were to actually look at a graph of this, which is always handy to do, you would get that as you're approaching 4, from the negative side or the left side or the right side, we will in fact be approaching the value of 8. Okay. There's other types of questions that limits deal with as well, and so let's do some of those as well. Well, let's actually talk about some properties first. Through all this, we've discovered many properties have been discovered. We can talk about constants. What's the properties? What's the limits of constants? So we're going to call your limit as x approaches a of your constant will always just equal your constant. Okay, so I guess that's a horizontal line. Just the most simplistic function as x approaches a of x, this will equal a. Whatever a is, that's what it is. And so we kind of already looked at that on other ones as well. So that wasn't too bad. A couple of the other ones that are really kind of handy to look at are what happens when you are multiplying these together. We can look at the property of multiplication, where if I have two functions, f of x and g of x, and if I'm taking the limit as x approaches a of f of x, I should be using square brackets there, f of x times g of x, this is just equal to the limit of each of them multiplied together. And this is incredibly handy if you have maybe f of x is a much simpler function, g of x is a much more complicated function, and so there's a lot more work to do on the g of x. Well, it's nice to be to split them up, and then we can multiply them together later. Okay, so these are some properties, and the same property works for division. If you're dividing these things, if you're dividing f of x and g of x, you want to know what the limit is at x as x approaches a. You can just find the limit of each and then divide them together afterwards. And so those are just a few of the properties that have been derived, and might leave it later on as exercises to prove that these in fact are true, maybe. We'll see. But there are some other really important type of functions that we want to look at for how do we evaluate the limits of these. And the trick behind all of the limits is really understanding your algebra. And so let's talk about this question here. The limit as x approaches 0 on x plus 1, the square root of x plus 1 minus 1 all over x. And we can quickly see, put x into the denominator, this won't work. Also, if you put x in the numerator, you get square root of 1, which is 1. 1 minus 1 is 0. So this, in fact, would become 0 over 0, which doesn't work. And so what we need to do is find a way, can we maybe work this through algebraically? How can we solve this? And so what we want to do is just multiply this whole thing by 1 over 1. Right? That doesn't change anything, that doesn't hurt. But instead of saying 1 over 1, let's write out in a slightly different way. Let's multiply the tops together, but instead of doing minus 1, let's do plus 1. And if you do that on the top, you do it on the bottom. And this is called rationalizing the denominator, or the expression. And so the reason why I choose plus 1 here is this is a binomial, that's a binomial, and we know difference of squares. If one's a minus, one's a plus, you get no middle term, which will really help us out. And so we're going to go ahead and multiply all this through. And so this is just the limit then, as x approaches 0. If you were to multiply those together, you would just get x plus 1 minus 1 all over x times the square root of x plus 1 plus 1. Okay? Well, does this really help us yet? Are we where we need to be?